This is the 14th video in our series on topology. And in the previous couple of videos, we wrapped up our section on different types of connectedness of topological spaces. Be that connectedness by the precise definition or the notion of Hausdorff, which is kind of like a notion of connectedness, or the idea of path connectedness, which again is another type of connectedness within topological spaces. And now we're going to move on to the notion of compactness within topological spaces. Now, of course, that's going to require a couple of setup definitions, so let's look at those. So a collection of subsets of X. So we've got this script A is a subset of the power set of X. So that means that, well, A is a set of subsets of X. Okay, so anyway, this script A is said to cover X if X is equal to the union over all of the elements of A. So that's how I've written that here. So the union over all little a and, big A and script A of the set A. Okay, now we need the notion of an open cover, which is simply a cover that also has only open sets. So here we've got this calligraphic U is called an open cover of X if this calligraphic U covers X, and every element of this script U is an open set of X. Okay, then finally we're ready for the idea of a compact set or a compact topological space. So we say that X is compact if for all open covers of X, we'll call those U, we can find finitely many sets, U1 up to UN in script U, where X is equal to the union of the U1 up to UN. So generally the way that we think about this verbally is every open cover has a finite subcover. That's what's going on here. We've got our open cover U, which is arbitrary, and the compactness allows us to find a finite subcover, this U1 up to UN of our open cover. Okay, so as we'll see, it's a little bit easier to show things aren't compact in general than it is to show that they are compact. So we're going to start by showing a couple of things are not compact, starting with the real numbers. So look over here at the definition and note, in order to show something is not compact, we need to find an open cover that does not admit a finite subcover. So that shouldn't be too bad. Okay, so let's say U is equal to the following set, and it's going to be the set of the intervals n minus 1 to n plus 1 as n runs over all integers. So we can graphically represent that as follows. So let's get some integers on the board here. So 0, 1, 2, 3. Let's put -1, -2, and -3 here. So let's observe that we've got a set from -1 up to 0. Or sorry, -1 up to 1. So that would be the n equals 0 set, if you will. And then we've got a set from 0 to 2. That would be the n equals 1 set. I'm going to put it over the number line, even though it's sitting on the number line there, just so that it doesn't blend in. And then we've also got the set here from, let's see, 1 up to 3. Then we've got our next set, which is going to go 2 up to 4. And then we've got some stuff happening in the reverse direction as well. Okay, so anyway, it's pretty easy to see that these intervals form an open cover of the real numbers. But I'd like to claim that there is no finite subcover. So let's take any finite set of U. But notice that any finite set of U will look like this. It'll be n sub k minus 1 to n sub k plus 1, where maybe k goes from 1 to capital N. So it's got to have finitely many of those things. So what we're doing is we are just finding a subsequence of integers that builds that finite set. But now let's observe that if we take the union here, so this would be the union from k equals 1 to n of n sub k minus 1 to n sub k plus 1, we pretty clearly do not contain all real numbers. We can actually construct a real number that we don't contain here. This does not contain the maximum of n1 up to nk plus 2. Pretty clearly, that maximum of n1 up to nk plus 2 is not an element of any of these intervals. Guess we didn't really need to add 2 there. We could have added 1. And so since it's not an element of any of the intervals, it's not in the union of the intervals, which means the union of these intervals is not the real numbers. But any finite subset of U will look like this. So what have we done? We've just constructed an open cover that does not admit a finite subcover. Okay, so now let's look at the interval from 0 to 1, not including 0 or 1. We're going to show that this is also not compact. And so we need to do the same kind of thing. We need to start with an open cover and show that it does not admit a finite subcover. So this is not too bad either. Let's take our open cover to be the set or the set of intervals from 1 over n to 1 as n goes over all natural numbers. And so I think it's pretty clear by some stuff that we did much earlier in the course that if we take the union over all of these intervals, which we could write as the union over all n in natural numbers of 1 over n to 1, we definitely get the interval from 0 to 1. So this is a cover. Now we just have to show that it does not admit a subcover. Okay, so let's take any finite subset of this open cover and notice that it's going to be of the following form. It'll be 1 over n sub 1 comma 1, 1 over n sub 2 comma 1, dot 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 1 over n sub, let's say k comma 1. So there are k elements of this finite set. And I guess without loss of generality, let's maybe order these things. So n1 is less than n2, which is less than n3, so on and so forth. nk is the smallest one of these. And now let's observe that if we take the union here, so this is going to be the union as I goes from 1 to k of 1 over n1, or sorry, 1 over ni up to 1, you'll see that since n sub k is the biggest one, this 1 over n sub k gets the closest to 0. And so since these are nested, we necessarily have this as 1 over n sub k plus 1. But we can construct something that is not inside of this interval as well, and that would be, for instance, 1 over 2 times n sub k. So that 1 over 2 times n sub k is in the interval from 0 to 1, but not in our union. And it's important here that we took an arbitrary finite set from our open cover to show that we did not have compactness here. So that means that, again, we found an open cover that does not admit a finite subcover. Okay, so let's look at a couple more examples. Okay, so now we're going to do one more example of something that's not compact before showing something is compact. So let's consider the set of reciprocals of natural numbers. And we're going to consider this as a subspace of R, and so we're going to give it the subspace topology. And we're going to show that this is not compact. And just for reference, this set X is 1, half, third, quarter, so on and so forth. Now, I'd like to observe that if we take this interval here, starting at 1 over n minus 1, and go all the way up to, or sorry, that should start at 1 over n plus 1, and go all the way up to 1 over n minus 1, that is going to contain the element 1 over n. And it doesn't contain anything else from our set X. So let's maybe observe the following, and that is that the singleton 1 over n is open in X, given the subspace topology. And why is that? Well, that's because the singleton 1 over n is pretty clearly equal to the interval 1 over n plus 1 to 1 over n minus 1 intersected with X. And then that open interval is open in the real numbers, but that's exactly what it takes to be open in the subspace topology. Okay, but then What does that mean? That means we have an open cover, which I'll call U, and it'll be simply the set of all of these singletons. So it'll be the set of all singletons 1 over n, as n runs through all natural numbers. Okay, so we've got that that is an open cover. But does that admit a finite subcover? Well, no, it doesn't, because any finite set of this will have the following form. So it'll be 1 over n sub 1, 1 over n sub 2, or sorry, those should all be singletons. So it'll be the singleton of 1 over n1, the singleton 1 over n2, up to the singleton of, for instance, 1 over nk. But of course, we can find a 1 over something that is not exhibited in any of those singletons there. And that element is an element of the original set, but not an element of our finite subcover. So I guess we could note that here. So we can pick a 1 over m in x such that m is not equal to n sub I for all I going from 1 to k. But again, I guess I'll just say this in words. That means that we have built an open cover that does not admit a finite subcover, meaning we do not have a topological space here that is compact. Now I'd like to point out here one thing that we're going to do for this example and probably the next example, but we will stop doing it eventually, and that is talking about this thing being open in the subspace topology. We won't actually need that anymore. We'll just take an open set in the bigger space and then use the fact that our open cover contains our original space instead of is equal to our original space. I guess I should say the union of our open cover. So we'll see that change when we get to it. Okay, so now let's move on to a next example, which is going to be built off of this, and that is x bar, where x is this thing up here. So let's observe that x bar is 1 over n, as n goes through all natural numbers, union the singleton 0. And I think that's pretty clear because x bar is the closure of x and 0 is clearly a limit point of x, and in fact it's the only limit point of x. We probably actually did that as an exercise previously. Okay, so now in order to show that this is compact, we need to show that if we take any open cover, we can construct out of it a finite subcover. So let's do that. So let's suppose that U is an open cover of x bar. But what does that tell us? Well, that tells us that there exists some V inside of U, which is open such that 0 is an element of V. So how did we get that? Well, if U covers x bar, then that means the union of all of the sets inside of U is equal to x bar. But 0 is inside of x bar, so that means 0 must be inside of one of those sets from U. Okay, great. But then, since we're working in the subspace topology with the real numbers, that means that there exists some sort of open set U, which is an open set of R, such that V is equal to our set x bar intersected with our set U. Okay, but then using the openness in the real numbers, that means that we can get a delta bigger than 0 such that the interval minus delta to delta is contained inside of U. And this is where things are going to start to come together. Since delta is bigger than 0, we know that delta will be larger than all but finitely many reciprocals of natural numbers. And we can see that as follows. Let's take a capital N, which is a natural number, such that 1 over capital N is less than delta. So, well, we've done this kind of thing many times already. We have a small real number, delta in this case, and we can always find a reciprocal of a natural number that is smaller than that small real number. Okay, so well, what does that tell us? Notice For all natural numbers bigger than capital N, what do we have? Well, we have 1 over little n is less than 1 over big N, maybe less than or equal to 1 over big N, which is less than delta, which tells us that 1 over little n is inside of U. It tells us it's inside of U because it's pretty clearly inside of this interval minus delta to delta. But then since it's inside of the interval minus delta to delta, it has to be inside of U. But then all of these 1 over n's are also inside of x bar. So it's inside of U intersected with x bar. But U intersected with x bar is equal to V by our construction up there. So now what do we have? Well, let's note the following, and that is that 1 over capital N, 1 over capital N plus 1, 1 over capital N plus 2, so on and so forth, are all contained inside of V. But that leaves finitely many elements of x bar that are not inside of V. But again, we know that they have to be inside of one of the elements of the open cover because this is an open cover. So let's find those places where they are. So let's find, I'll call it V1 up to V sub capital N minus 1, such that 1 over m is inside of 1 over V sub m for all m going from 1 up to capital N minus 1. Okay, so that's again by the covering property of this U. All of these V's are inside our U. Okay, and so now let's notice that we're essentially done because we've got X is equal to V union V1 union V2 union all the way up to V sub n minus 1. So we've constructed our finite subcover. Okay, so that's our first set that we've shown as compact. Now let's show that another set is compact. Now we're going to show that the closed interval from 0 to 1 is compact. Observe that the open interval from 0 to 1 was not compact. And this example can really serve as some sort of model to show that any closed interval, well, any closed interval that is not infinite is also compact. But in fact, we don't quite have that yet until we have compactnesses preserved under homeomorphisms. Really just under images of continuous maps, but we'll see that later. Okay, so anyway, to the proof that the interval from 0 to 1, including 0 and 1, is compact. So let's let U be an open cover of 0, 1. And our goal here is to construct a finite subcover, or maybe prove that a finite subcover must exist. And so let's do that by taking a set capital A to be the following set. It's going to be all numbers x from the interval 0 to 1 such that there exists U1 up to UN inside of U. The interval from 0 up to x, including both, is contained in U1, U2, union, all the way up to UN. So what have we done here? Well, we've looked at all subintervals of 0, 1 that start at 0, where those subintervals admit a finite subcover. And we've just called all of their endpoints x. Okay, great. So now let's maybe look at a couple of quick observations, and that is that A is non-empty. So I think that's pretty clear because 0 is an element of A. And we can see that because the interval from 0 to 0 is simply the singleton 0. But the singleton 0 is going to admit a finite subcover. You just take whichever open set contains 0. Now, let's also note that A is going to be a subset of the interval from 0 to 1. But that means that it's bounded above. Now, it's clearly a subset of the interval from 0 to 1 because, well, it's only containing elements from 0 to 1. So let's see what we've got. We've got a non-empty subset of real numbers that's bounded above. But let's recall by the least upper bound property of the real numbers, that means that this set has a least upper bound. In other words, it has a supremum. So let's call that supremum A. So we'll set A equal to the sup of capital A. And then, well, let's notice that the following is pretty clear, and that is A comes from the set from 0 to 1. I think we can pretty clearly see that the supremum of A will be less than or equal to the supremum of 0, 1, but the supremum of 0, 1 is 1. So that means that A has to be there. Okay, so now let's break this into some cases. So our first case is what happens if the supremum is 0? So that would be maybe the worst possible scenario. Okay, so now let's find a U in U such that 0 is inside of that open set U. But then since U is open, there exists a delta bigger than 0 such that the interval minus delta to delta is contained inside of U. But that means that U, in fact, covers the set from 0 to delta over 2. Because notice that, well, if this interval from minus delta to delta is contained inside of U, well, then U definitely contains 0. Well, actually, it contains everything between 0 and delta over 2, including both. But that means that delta over 2 is an element of A, because notice this 0 to delta over 2 has a finite subcover, simply U itself. So we've got delta over 2 is an A with delta over 2 is strictly bigger than the supremum of A. But it's impossible to have something inside of a set that's larger than the supremum of that set by the definition of the supremum. So we get a contradiction there. So, well, what does that mean? This first case is impossible, meaning that A cannot be equal to 0. Now let's move on to the second case. So we'll say case 2, and that is that A is from the interval from 0 to 1, not including 0 and not including 1. We've already taken the A equals 0 case. Now we're going to work towards a contradiction here as well, and that's because, well, we want A to be equal to 1. So if we show that it can't be equal to 0, and it can't be on this open interval, then it has to be equal to 1. That's the only scenario that's left after those two cases. Okay, great. So now what do we want to do here? So let's do the same kind of thing. So now let's find something that I'll call a U0, which is in our open cover, such that we have A is an element of U0. Okay, so that's always possible because we have an open cover in the first place. But now U0 is open, we know that, so that means that there exists a delta bigger than 0 such that A minus delta to A plus delta is contained inside of this U0. So I've reset my value of delta from the previous case to this case. I'd also like to point out here that we're not worrying about the subspace topology versus the topology of all of R here. We could worry about the subspace topology and say that all of these are open in the interval from 0 to 1, and then bring those into open sets in R intersected with the interval from 0 to 1, but that's not really going to add anything. It's kind of enough to do this. If you'd rather work in the subspace topology, you can just kind of in parallel to the couple of previous examples, mimic putting everything into the subspace topology with intersections of all of these open sets with this closed interval up here. But that's kind of neither here nor there. Okay, so anyway, we've got this interval A minus delta to A plus delta inside of U0. But now let's note the following. So since A minus delta is less than A, that tells us that A minus delta is inside our set capital A, which means the interval from 0 to A minus delta has a finite subcover. Because, well, why is that? Well, remember, the things from capital A were exactly those intervals that admitted finite subcovers. So I'll call that finite subcover U1 up to UN. Okay, nice. But now let's look at the union of U0 with U1 with U2 with all the way up to UN. And I want to observe that there's some interval which is a little bit too big inside of this union. And that interval starts at 0 and goes to A plus delta over 2. Now, why is that? Well, all the way up to A minus delta, we are inside of this union right here by the fact that we had this finite subcover. And then from A minus delta all the way up to A plus delta, we're inside of this bit right here. But if we truncate that before A plus delta at, for instance, A plus delta over 2, it's going to include that endpoint. So anyway, we've got a finite subcover for this interval from 0 to A plus delta over 2. But what does that mean? That means that A plus delta over 2 is inside of our set capital A, because that's the entry fee to be inside of our set capital A. But again, we've got a problem here, because that means that A plus delta over 2 is bigger than A, which A was the supremum of A. But you can't have anything inside of A larger than the supremum. That's against the definition of being an upper bound in the first place. So that brings us to a contradiction. So let's see. We've contradicted the ability of A to be equal to 0, or for A to be between 0 and 1, not including 0 or 1. Then we argued up here why it had to be on this closed interval. But all those things together tells that A has to be equal to 1. Well, I guess there's one last thing to show, and that is that A itself contains its supremum in the first place. But maybe I'll leave that as a bit of a homework exercise. So if A contains the supremum, and the supremum is equal to 1, then that means that our set 0 to 1 admits a finite subcover for any open cover, but that means it's compact. Okay, so now I want to finish the video by doing a couple of maybe more general results involving compactness. Okay, so the next proof is going to really give us some intuition about compactness, as compactness is like a beefed up version of a set being closed. And so let's see. If we've got X is a compact topological space and A is a closed subset of X, then A is compact. Okay, so let's see how the proof goes here. So let's suppose we have an open cover of A. So of course we need to start with an arbitrary open cover of A and then construct a finite subcover. So we've got an open cover U of A. But now somehow we want to use the fact that X is compact. But let's see, can we expand this open cover of A to an open cover of X? And we can pretty easily. So let's consider the following extension. So I'll call it maybe U, well, maybe U prime isn't great because we've got the prime means limit points, maybe U hat. And that's going to be equal to U unioned with the set X minus A. So notice that X minus A is, well, most definitely open because A is closed. And remember, the complement of a closed set is open and vice versa. And then, well, let's also notice that this is an open cover of X. So it contains all open sets because it's the union of this, which only contains open sets, and that, which is a singleton of a single open set. Now, why does it cover X? Well, notice that this U right here covers A, and then this thing right here covers everything except for A. So if you smush those together, it's going to cover all of X. But now notice that there is a finite subcover. So our finite subcover will be of one of the following forms. So the compactness tells us that the finite subcover must exist, but it might look a little bit different. So it might either be U1 union U2 all the way up to UN, or it might be U1 union U2 all the way up to UN and then union with X minus A. So if we take a finite subcover from this set right here, well, there are two possibilities. The sets can come from only this script U, or they can come from the script U and the thing that we added on. So that means that, well, those are the two possibilities of the subcovers. And I've put unions between them instead of commas, just to recall that that's exactly what it means to be a finite subcover, is that they union to contain the whole space. But let's notice that either way, we have X is equal to U1 union U2 all the way up to union UN unioned with X minus A. Now, perhaps we didn't need the X minus A, or perhaps we did. But if we union it on, it's not going to change anything. It's still going to cover all of X. Okay, and I guess like I said this out loud, but let's maybe put it here so that we have it, and that is that UI is an element of this cover of A, which is U. And now let's note that since this is covering all except for A, that means that this bit right here has to cover A. So let's maybe do a little observation of that, and that is A is a subset of U1 union U2 union all the way up to UN. Great. But then what does that mean? Well, that means that this collection, U1 up to UN, is a finite subcover of A. So we started with a closed set inside a compact space, an arbitrary open cover of that closed set, and we were able to construct a finite subcover. That's exactly what it takes for A to be compact. All right, let's do one more general result before I leave you with some exercises. All right, for our last result, we'll say that if we've got a Hausdorff topological space X, and then we've got a compact subset of X, which we'll call Y, then necessarily Y is closed. But let's quickly recall that Y is closed if and only if the complement X minus Y is open. That's the definition of a closed set. Then what does it take to be an open set? Well, a set is open if you can always find a neighborhood of every point inside of that open set that is contained in the open set. So that's exactly what we're going to do here. So let's suppose that X is inside of X minus Y. And then, well, let's sketch out what we want. So we want a neighborhood of X that is inside of X minus Y. That's what it takes for X minus Y to be open. Okay, so now since X is Hausdorff, we have to use that, of course, because that's our given. For all Y in Y, there exists open sets. I'll call them maybe UY and VY, such that we have X is inside of UY, Y is inside of VY, and UY intersected with VY is empty. Recall, that's what it means to be Hausdorff. You can take any two non-equal points and get them in non-intersecting open sets. Now, how do we know that little x and little y are not equal? Well, notice little x is outside of y, but little y is inside of y. And notice that we did this for all elements of our y. Okay, great. But let's note the following. We have an open cover of y. We've just constructed an open cover of y. And what is that open cover? Well, it's Vy as little y runs through all of y. Great. Then do we want to give it a name? I don't know that we need to give it a name, but let's call it capital script V. But we assumed y was compact. We've got an open cover of a compact space. That means that we have a finite subcover. So there exists Vy1, Vy2, all the way down Vyn, which are inside of our open cover, such that y is a subset of the union of all of these. So Vy1 union Vy2 union all the way up to Vyn. Okay, great. And now let's notice that all of these Vy's have a companion, those Uys. So now we're going to use those. And we're going to use those via their intersection. So let's set capital U equal to the intersection Uy1 with Uy2 intersected all the way up to Uy sub n. Okay, great. And now let's note that for all little y in y, we know that x is in u little y. But that means that x is inside of this u. Well, because it's in each of these, so it's going to be in their intersection. That's the definition of intersection. And now I'd like to finish this off with the following observation. And that is, if we take u intersected with y, we get the empty set. And let's see why that is. So otherwise, we would have something, maybe we call it z, inside of u intersected with y. But let's observe that that means that z is inside of uy sub k for all k going from 1 to n. And z is inside of Vy1 union all the way up to Vyn. But z being in that union means that there exists an m such that z is inside of v sub y sub m. So we're playing unions and intersections off of each other here. So since it's in this u, and this u is an intersection of all of these u's, that means it has to be in all of those u's. That's what we have here. But then since z is inside of y, and y is a subset of the union of the v's, it must be in at least one of the v's. So that's what we have right here. But let's observe that this m is definitely in one of these indices here. But what that tells us is that z is inside of u sub y sub m intersected with v sub y sub m. But we assumed that to be an empty set. Or I guess we constructed it to be empty set by this construction right here, built off the Hausdorffness of the space. So, well, that maybe contradicts our ability to get something inside of this intersection, meaning that this intersection is empty. But now we're essentially done, because this intersection being empty means that u is contained in x minus y. So let's see what we did here. We took an arbitrary x in x minus y. Then we found an open set u. We know that u is an open set because it's the intersection of finitely many open sets. So we found an open set u that is a subset of x minus y that contains x. But that's exactly finding a neighborhood of x that's contained in x minus y, meaning x minus y is open, meaning y is closed. Okay, so that's the end of that proof, and now I'm going to leave you with a couple of homework exercises. All right, so here's some exercises. So the first, let's take any non-empty set x and endow it with the finite complement topology. So let's recall in that topology, all the closed sets are either the empty set, the whole set, or finite sets. So x is the only potentially infinite closed set. And then our goal is to show that every subspace y of x is compact. In particular, x is compact. So now let's show that the following are not compact. The first one is the half open interval from 0 to 1, including 0 but not 1. Next is the rational numbers. And then finally, the set of all continuous functions from 0, 1 to r. And we're going to endow that with the metric topology, where our metric is df of g, so the distance between f and g, is the integral from 0 to 1 of the absolute value of f of x minus g of x dx. And that's a good